Hi, in this video we're going to look at how to approximate the area under a curve using a Riemann sum with left-handed rectangles. For our example, we're going to use the curve y equals 0.5x squared plus 2, which is shown here in blue, and we're going to approximate the area under that graph on the interval x element 0 to 4 using a Riemann sum with 4 left-handed rectangles. So the first thing I would like to do is draw in a vertical line at x equals 4 up until it meets my curve. So this is the space that we're talking about. It's north of the x-axis, it's to the left of x equals 4, it's below the curve y equals 0.5x squared plus 2, and it's to the right of the y-axis. So here you can see it shaded in yellow. So my next thing that I would like to do is draw in some partitions that are going to separate one rectangle from the next. Now because I want to use 4 left rectangles, and my region overall is 4 units wide, I'm going to take the width of my entire region and divide it by the number of rectangles. So since they're both 4, 4 divided by 4 is 1, so each rectangle will be 1 unit wide. So here are my partitions. I'm drawing in one at x equals 1, another one at x equals 2, another one at x equals 3, and my last one will end here at 4. Now I need to draw in my tops. The tops of my rectangles, because these are not rectangles yet, will be parallel to the x-axis. And what I want to do is follow up the left-hand side of the curve, or the left-hand side of the region, always, to form my top. So from 0 to 1, the left side is at x equals 0, and the right side is at x equals 1. Since I'm asked for left rectangles, what I'm going to do is follow up the left-hand side until I meet the curve, and then draw in my top. And then same here, at x equals 1, that's the left-hand side. Come straight across until I parallel to the x-axis until I meet the next partition line. Repeating this, you can see what my 4 rectangles look like. Now these rectangles, besides being left, also happen to be inscribed rectangles because they fit entirely inside the region. Next, I would like to color them in so you can see the green rectangles are what I'm going for. If I could add up the area of all 4 of those rectangles, I would be pretty close, but I would have an under approximation to the true area under the curve, because you can see the yellow spaces that I would be missing. Now next I'm going to name these rectangles. I'm going to call this one a sub 1, the second one a sub 2, the third one a sub 3, and the last one a sub 4. And what I would like to do is say my area is approximately equal to the sum of a sub k as k goes from 1 to 4. So this is really saying add up the 4 rectangles. We're going to start at the lower limit, a sub 1 plus a sub 2 plus a sub 3 plus a sub 4, which again are those green rectangles over here. And again, you can see the left corner of that rectangle, the left upper corner, is hitting the curve each time. The right corner does not hit the curve. If I was looking for right rectangles, then I would make sure that the right corner was the one hitting the curve. So, expanding my summation, again, I have a sub 1 plus a sub 2 plus a sub 3 plus a sub 4. Well, now I need to find the areas of each of these rectangles. Well, I know to find the area of a rectangle, I multiply base times height. And I know the base for each rectangle is 1. But the heights, I can see that they're getting bigger as I go to the right. So the next thing I want to do is locate the coordinates of the corners, the left corners that are meeting the curve. Now where did I get 0, 2, 1, 2.5, 2, 4, and 3, 6.5? By merely plugging in the x coordinate into this equation. So when x is 0, and I follow that straight up, 0.5 times 0 squared plus 2 is 2, and that's my y coordinate, so that's the height of this first rectangle. It's 1 unit wide and it's 2 units tall. The second rectangle, well, I can see here if I follow up x equals 1 until I meet the curve, The y-coordinate is going to be 2.5 because if I plug 1 in for x, square it, multiply by 0.5, I have 0.5 plus 2 is 2.5. That's the height of the second rectangle. For the third rectangle, again, I have a decision to make. Do I plug in 2 for x or 3 for x? Well, if I wanted right-hand ones, I would plug in 3 right now. But since I want a left, I'm going to take the left side of the region, which is x equals 2, plug it in here, and what I get out is 4, so that's the y-coordinate there. So that's the height of the third rectangle. And for the last rectangle, because I'm using left-handed rectangles, I won't be using the right edge of the region, so I won't be using x equals 4. But I will be using x equals 3 because that's the left side of this last rectangle. If I take 3 and plug it into my equation, I get 6.5. So now I'm basically done. For the 4 rectangles, the first rectangle is 1 wide and 2 units tall. Again, I'm using the y-coordinate. Plus, the second rectangle again is 1 wide and 2.5 units tall. The third rectangle is 1 unit wide and 4 units tall. And the last rectangle is 1 unit wide and 6.5 units tall, which gives me a grand total of 15. So these 4 rectangles, area is equal to 15. I know the true area is somewhat more than 15. Exactly how much more than 15, we don't know. We could figure it out using calculus, but in essence, what we'll want to do is increase the number of rectangles. As we increase the number of rectangles, we'll get a closer and closer approximation to our actual area. Here's a nice program for a visualization of what we're talking about. In this upper quadrant, we're going to have left Riemann sum. Over here, we're going to have a right Riemann sum. Here we'll have midpoint, and here we'll have a trapezoidal approximation. And as I increase the number of rectangles, and the limit of this program is 100 rectangles, you can see how closely the rectangles now approximate the area under the curve, whether I'm using left, right, midpoint, or trapezoidal. The one that comes out the best in this case was midpoint. That usually is the case. In this case, we don't know really which one would be an under approximation or over approximation other than the program tells us, because you can see some of the left-hand rectangles under approximate the region while other ones over approximate. You can see the corners sticking out. It'll actually be a little bit easier if I back up the number of rectangles. So here, with fewer rectangles, each one's a little bit wider, so you can see the first 4 definitely under approximating, even the 5th one slightly under approximating, and then here you can see some of these ones over approximating. Now, the true area under this curve is 216.66 repeating. This one came up 207, so it's under approximating by about 9.33. This right Riemann sum is over approximating by about 10. The midpoint Riemann sum is barely off. It's only under approximating by negative 0.173, and the trapezoidal approximation is off by 0.348. So again, the midpoint Riemann sum approximation is the best. But watch what happens to the errors. You'll see these errors approaching 0. Keep your eye on any one of them. As the number of rectangles increases, our errors all went down. So you can see these are now off by about 3 apiece. The midpoint now is only under approximating by negative 0.016. As a relative error, that would be very small because, again, the true area is 216.6 repeating. This turned out to be 216.65, very close to the actual area. And the trapezoidal approximation is also very close. And so there you have it. That's all there is to it. Split your region up into equally wide spaces with the right number of rectangles, and then compute the y-coordinates to get the heights of each rectangle, and then simply multiply base times height and add them all up. And that's everything that you need to know about approximating areas under curves using left-handed Riemann sums. Thanks for watching.